Today we are going to discuss gravitational field intensity. What is the difference between gravitational field and gravitational field intensity? And then we'll see what is the expression for gravitational field intensity, how it is related with acceleration due to gravity. Then we'll discuss what is gravitational potential and what is its expression. We'll also derive the expression for gravitational potential energy. And finally, we'll discuss escape velocity. What is escape velocity and how we can get the expression for escape velocity, on what factors it depends. So all these we'll discuss in today's discussion. Gravitational field. It is the space surrounding a given mass up to which it can exert force on any test mass. So suppose you have a body of mass m, and if we consider that it can exert force on a test mass delta m up to a distance r. So taking this r as a radius, if you construct a sphere, in that case, this will be the gravitational field of this mass capital M. Because if the test mass is experiencing force up to the distance r, that means this is the boundary there. So if test mass is within this, in that case it will experience force. If it is outside, it will not experience any force. So that will be the gravitational field there of this particular mass. But now if you consider that what is this particular distance r? So expression for the force will be how much? It will be your gm delta m by r square. If we say that this r gives the boundary of that field, that means up to this particular distance it will experience force. So that means at r the value of force will be 0. So if f is 0, then what should be the value of r there? It is your gm delta m by r square, which is 0. This capital M is fixed, delta m is fixed, capital G is fixed, so r will have the value infinity. So only if the r has the value infinity, the force will be 0. And remember that this r which we are getting, it will be same whatever be the value of this capital M. So it means the field due to any mass will extend up to infinity. So if the field of all masses is extending up to infinity, if you have to distinguish the field produced by one mass from the other one, definitely this concept of gravitational field is not the sufficient one. We need some other parameters by which we can measure the strength of that particular field. And that we call it as the gravitational field intensity. Gravitational field intensity we define as the force experienced per unit test mass placed at that point. So gravitational field intensity at a point is the force experienced per unit test mass placed at that point. So in that term, we find out what is the gravitational field intensity at that point. So suppose I have to measure the value of gravitational field intensity due to this mass at a distance r. So in that case, what is the force experienced? So force experienced is your gm delta m by r square. So force experienced per unit test mass, because this is the force experienced by the test mass delta m per unit test mass, that will be your F by delta m, and this will be gm delta m by r square into 1 by delta m, that is your gm by r square. Now by definition, because we have said that force experienced per unit test mass will be the gravitational field intensity. So the gravitational field intensity will be your Gm by r square. And remember, this will be definitely a vector quantity because it is the force experienced. And what will be its direction? It will be definitely directed towards the given mass there. So in that case, this will be the direction of the gravitational field intensity there. Now you can also notice that this expression of the gravitational field intensity is also same as acceleration due to gravity, because the acceleration due to gravity expression also was same Gm by r square. So the gravitational field intensity is numerically equal to acceleration due to gravity at that particular point. So that is how you can correlate gravitational field intensity with acceleration due to gravity. And if you consider its unit, or you can say SI unit of this is your Newton per kg force per unit test mass, or it may be your meter per second square. So this is how you can get the expression for the gravitational field intensity as well as its unit here. In its definition of the gravitational field intensity as well as that of the gravitational field, we have used the word test mass. We have said that this delta m is the test mass there. What is this test mass? Test mass we take as a mass whose magnitude is very, very small. So delta m tending to 0. This particular test body will have the mass negligibly small. Why do we take it like that? If you consider that we want to find gravitational field intensity at a point, and there it is the force experienced per unit test mass placed at that point. Just imagine I have a body that is the test mass there of mass 10 kg. And this one is experiencing, suppose delta m is 10 kg and the force experienced is 100 Newton. So what will be the gravitational field intensity? If you take the gravitational field intensity, it is force per unit test mass. So if it is your F by m, delta m, so it will be your 10 Newton per kg. If our test mass is suppose your 1 kg, then how much force it will experience? This one, whatever be the source mass, I'm changing is this mass to say 1 kg. So obviously the force experienced will also get changed. Now this will be how much? 10 Newton. So the corresponding value of the gravitational field intensity will be again 10 by 1. So it is this much Newton per kg. If I take this delta m as 0.5 kg, then how much will be the force? This will be 5 Newton now. So in this case, gravitational field intensity, again it is your 5 divided by 0.5. So it is your once again 10 Newton per kg. Now what I'm trying to say, this mass which we are using to measure the gravitational field intensity, what we are calling it as the test mass, whatever mass I am taking, whether 10 kg, 1 kg or 0.5 kg for the given source mass there, we are getting the force changed. But if you consider the force per unit test mass, it is always same. So whether it is the mass 10 kg, 1 kg or 0.5, in all cases you are getting the same value of gravitational field intensity. So if it is such, why we should take this delta m tending to 0? Because for all cases you are getting whatever mass you are taking there, force per unit test mass, if you consider, it will always be same. It will not depend upon what initial mass we have taken for the test mass there. So why we should take this delta m very, very small? Now the reason is, suppose our source mass is m and I want to find its gravitational field intensity, suppose at a distance of 2 meters. So what is the way to calculate gravitational field intensity? I will bring test mass here at this particular position. We'll find out what force it is experiencing, and then force per unit test mass will give you the value of the gravitational field intensity at that point. So suppose capital M, which is the source mass, is kept at particular position. I want to know what is the field intensity at 2 meters from it. So I will be bringing a test mass at this particular point. So it will be 2 meter distance from that source mass. Suppose 2 meter point is here. So in this particular case, as you are bringing the test mass will experience force. And the force experienced by the test mass will be gm delta m by x square or r square, whatever you take. Suppose this is your r square. So this is the force experienced by the test mass. But remember, it is not that only test mass is experiencing force. It is the source is also experiencing force. So this one and the force will be experienced equal in magnitude by both. So it is possible that the source may get displaced from its original position due to the force which it is experiencing due to this test mass. So it may not be exactly at 2 meter distance. Like I'm trying to focus at the particular point, initial point, which was 2 meter distant from the source mass. But as I'm bringing the test mass at this particular position, the source mass may come closer and it is now not exactly at 2 meter distance. So the force experienced will change, the gravitational field intensity value will change. So if you want that your measured value is as accurate as possible, then this F should be as small as possible. If the force experienced is as small as possible, then your source mass will get least disturbed. So what we can change? We cannot change G. G is universal constant. This M, source mass, this also we cannot change. If you want the gravitational field intensity due to 10 kg mass, 100 kg mass, you cannot change that one. So it is fixed. R, which is a particular distance where you want to find gravitational field intensity, this also you cannot change. So what is the thing which we can change? Definitely this delta M. So if this delta M is a small, the force will be small. And if the force is a small, our system will be least disturbed. And then we can measure the gravitational field intensity as accurately as possible. So this is the reason why we take the test mass negligibly small. And again here, negligibly small means what? See, a small term or bigger term or large term, it all depends upon the relative value. So it should be small as compared to our source mass. So if you consider the source mass there, in respect to that, the test mass should have a very, very small value. Like suppose if I take 100 kg, with respect to that, 1 milligram mass or test mass is very small. If you consider 1 kg stone or say 10 kg stone, but now you are comparing it with the mass of the sun or earth, in that case it is very, very small. So this 10 kg mass for earth will also be a test mass there. So basically we have to take the test mass, its magnitude should be very, very small as compared to the source mass. Next term is gravitational potential. Gravitational potential at a point is the work done per unit test mass in displacing it from infinity to the given point. You take a test mass, you displace it from infinity to the given point. Whatever is the work done per unit test mass, that will be the gravitational potential. So here, suppose our source mass is capital M and I want its gravitational potential at a distance r from it. Suppose I assume that we have a test mass delta m at any moment at a distance x from it. So this is suppose at a distance x. So this m is the source mass, and we want to find its potential, gravitational potential at a distance r from it. So we take a test mass delta m at a distance x at any moment. Suppose this is the point P where it is located. So the force experienced by test mass, how much it will be? It will be your gm delta m by x square. Suppose this mass gets displaced through dx. So if test mass is displaced through dx, therefore a small work done, that will be equals to how much? It will be your gm delta m by x square dx, because it will be your f dx. That is the small work done in the displacement through dx. So small work done in displacement or in displacing it through dx. So this is the small work done. So a small work done per unit test mass. A small work done per unit test mass. So this small work done will be divided by the test mass there. That is the mass of the test body there. So it will be your gm by x square into dx. That is the small work done per unit test mass. So if you want the total work done in displacing it from infinity to given point, I have to find that. So how much will it be? This will be the integral of this work, and it is from infinity to r. So this will be equal to gm, and this is your minus 1 by x r to infinity. This is minus gm 1 by r minus 1 by infinity, and this is equals to minus gm by r. Now, by definition, this work done per unit test mass in displacing it from infinity to given point, that is your gravitational potential there. So small work done for unit test mass, per unit test mass we have taken. So this is the expression. So by definition, gravitational potential will be how much? Minus gm by r. So this is the expression for a gravitational potential. This negative sign will indicate that as the mass is coming closer to the given mass there, or the source mass, it will be losing its energy, because at infinity its energy was 0. And since the gravitational force will be doing work, so it will be losing that energy. So that is why it is your minus gm by r. That means its energy has decreased by this amount, gm by r. So this is the expression for gravitational potential. And if you suppose want to know what is its unit, so unit will be equals to joule per kg, because it is the work done per unit test mass. So it will be joule per kg. Another term is there, gravitational potential energy. This is the work done for a given mass in displacing it from infinity to given point. Remember, gravitational potential was the work done per unit mass in displacing it from infinity to given point. But gravitational potential energy is the work done in displacing a given body from infinity to the given point. So in fact, you can easily understand that if you know what is the work done per unit test mass in displacing it from infinity to given point, in that case, if you have to find the work done for a given mass, we can simply multiply gravitational potential by the mass of the body, which is to be displaced. So let's see how we derive that one mathematically there. Derivation will be almost similar to what we have done for gravitational potential. This is the source mass, and suppose the given mass which we want to displace there is your small m, and this is at a distance x at any moment. We want the gravitational potential energy of the given mass capital M and the test mass there, which is a small m, at a separation r. So if you consider the force experienced by the given mass small m, that will be your gmm by x square. Now if this mass moves through dx, in that case a small work done in displacing it through dx, that will be gmm by x square into dx. And now if I have to find the total work done, because this was the small work done, so total work done in displacing it from infinity to given point will be simply gmm dx by x square integral from infinity to r. So it will be your g into minus 1 by x. Again we'll put the limit here, and then you'll get here this expression with the term small m there. So if you consider gravitational potential energy, in that case this one will have the term of the mass of the other body also. So it is your minus gmm by r. So this is the expression for the gravitational potential energy. Now you can see minus gmm by r was the gravitational potential, because this is your minus gmm by r into a small m. This is nothing but your gravitational potential into the mass of the body. So this is how you can get the gravitational potential energy there. And if you have to tell what is the unit of this, since it is the work done in displacing a given mass there, so it will be simply joule there. So the unit of this one will be equals to joule. Escape velocity. It is the minimum velocity with which a body must be projected to come out of gravitational field of a given heavenly body. Suppose you have a heavenly body there, or say you are taking Earth or any other planet. So from there, if you want to throw a body so that it comes out of its gravitational field, the minimum velocity with which the body should be projected, that is the escape velocity. So if you throw the body with the escape velocity, it will never come back in the gravitational field of that body again. So suppose we want to find its expression there. Suppose here we have the heavenly body, and suppose the given body of mass m at any moment, it is suppose at a distance x from it, and this body has a mass capital M. Say it is suppose Earth, its mass is capital M, radius is r. So here if we consider that we want its escape velocity from a particular point at a distance a, a particular point A at a distance r, and this x is the position of this one at any particular moment there. So again, in the same way, if you do force on the body M to be applied, because we have to apply a force which can overcome the gravitational force. So that will be gmm by x square. And suppose with this force we displace it through dx. So it is displaced dx from that. So in that case, a small work done in displacing it through dx. So that will be how much? It will be your f dx. So this is your f dx, which is your gmm by x square dx. If you want to find the total work done, so this will be equals to gmm dx by x square, and we are displacing it from r to infinity. It was initially at a distance r and we want to throw it to infinity. So that total work done will be gmm 1 by x, this is your infinity and r. So this is equals to minus gmm 1 by infinity minus 1 by r, and this is gmm by r, because 1 by infinity will be 0 and this negative and this one will become positive. Now let VE be escape velocity. So the kinetic energy to be imparted, that will be equals to how much? Half m VE square. This is the kinetic energy which we want to impart it so that it can do this much amount of work. Therefore, from energy consideration, if you take then half m VE square, this is equals to gmm by r, and that gives you VE is root over 2gm by r. This is the expression for escape velocity from a distance r from the center of the heavenly body. Now here, if I assume if small r is equals to capital R, then escape velocity will be root over 2gm by r, because the small r will be equal to capital R there. For Earth, if you take, then VE will be 11.18 kilometer per second, or roughly your 11.2 kilometer per second. That is the escape velocity from the surface of Earth. One more thing you remember and notice that this expression of escape velocity does not contain the term of the body to be projected. That means it is independent of the mass small m. So it means escape velocity will be same for all masses there. It does not depend upon the mass of the body to be projected. Of course, it will depend upon mass of the heavenly body from where we are throwing it, or from its gravitational field we are making it come out of it. So it will depend upon its mass, but not on the mass of the body which we want to throw. So this is the expression for escape velocity. For doing numericals on this gravitation, where we can apply the gravitational potential energy expression and the kinetic energy to be imparted to the body there, there is one simple method that you can apply for solving any numerical based on these datas. Like if it is said that with what velocity a body should be thrown so that it rises up to a height of 20 kilometer or 50 kilometer, you cannot use the formula V equals to root over 2gh. This is applicable for only small values of h over which you can consider g to remain same. But if it is said that a body is thrown so that it rises up to 50 kilometer, 100 kilometer, in that case, here you cannot use this formula. Similarly, if it is said a body is dropped from a particular height, what will be its velocity at another particular height there? Like if it is dropped from 200 kilometer, what will be the velocity at 100 kilometer from the surface of Earth? So there you cannot use directly the formula. So here, let's do that. Suppose this is Earth and we take that r is its radius, and this is the another point. Suppose this point is A, and this is the another point B, which is at a height h. What we are taking it from the surface of Earth, you can apply it for any case, that it may be at some other position there or at some other distance from the center of the Earth. So here, suppose it is this particular distance is h, and here from here we are throwing it with velocity say va, and it reaches point B with velocity vb. So for this case, if you consider that we have the body of mass m which we have thrown. So gravitational potential energy at point A, how much it will be? It is your minus, suppose if I assume the mass of the earth or heavenly body as capital M, so it is minus gmm by r. Kinetic energy at A, this is your half mva square. So total energy at A, this is your gravitational potential energy at A plus kinetic energy at A. So this is your minus gmm by r plus half m va square. In the same way, if you consider that gravitational potential energy at B, this is minus gmm by r plus h. Kinetic energy at B, that is half m vb square. So the total energy at B, this is your gravitational potential energy at B plus kinetic energy at B, which is equals to minus gmm by r plus h plus half m vb square. This is the total energy at B. This is the total energy at A. Now, if you apply conservation of energy, so by conservation of energy, what we get? Total energy at A same as total energy at B. So if you substitute, it is your minus gmm by r plus half m va square equals to minus gmm by r plus h half m vb square. M you can cancel from all these terms. Then in that case, it is your minus gm by r plus half va square equals to minus gm by r plus h plus half vb square. This you can use for a general expression for any particular problem related with the projection of a body from particular point or any given position there. And if you have to correlate what will be its velocity at one point or other point, you can use this one. Now this expression is very handy. You can use it for many cases there. Suppose I use it for derivation of the escape velocity. So for escape velocity, remember we say that it is the minimum velocity with which the body should be projected. So it means when it reaches point B, in that case, Vb should be equal to 0. And also, it should go up to the height which is infinity, where the gravitational potential energy will become 0. And how much we can write for Va? This we write it as your Ve, escape velocity. So if I substitute it here, minus gm by r plus r, this is equals to, this term will be 0, gm by infinity. So it is 0. Half mvb square, we have taken it 0. This is 0. So that gives you Ve equals to root over 2 gm by r. So from this also you can easily get. If it is said the body is projected with a velocity which is thrice the escape velocity. Remember, it is already there at infinity. It cannot go beyond that. So it will still be at infinity. But in that particular problem, there will be some kinetic energy even at infinity. That means there will be the body having some velocity there. So you can find out what will be the velocity of the body at that point, if it is thrown with a velocity more than escape velocity. Because the potential energy will be zero, but it will have some kinetic energy or velocity there. So you can use this one for finding any type of such problem. So this is how you can apply it for the different cases there, and especially for solving numericals based on this gravitation.